So what we saw in the first talk, we saw Shamir secret sharing scheme, threshold scheme, and we saw how to deal with corrupted parties in the reconstruction. When we say that if T is less than n over 3, Shamir secret sharing as is provides you both T privacy and you can reconstruct the secret with a 0 error probability. Now, in the second half of the talk, we're going to talk about what happened with how do we deal with a corrupted dealer. And this is verifiable secret sharing. What we have here, so here the dealer already in the sharing phase can provide secrets, they can provide shares that we have no idea if they actually lie on the same polynomial. What it means that when we come to reconstruct, we cannot even reconstruct the secret because there is no such, we cannot validate it. So the question is, can the honest parties validate or verify that the shares that they receive lie on the same polynomial of degree T, and again, T is less than 1/3 of the parties. So some security properties that we want, so sharing this time is not going to be just the dealer computes something, sends to the parties. Here it's going to be an interactive protocol. Parties are going to send messages to one another. The input of the dealer is the secret in this protocol, and all other parties have no input. We want to achieve privacy, that for an honest dealer, the adversary that controls less or at most T parties, it learns nothing about the secret S. We want to achieve consistency. Here it means that the output of the honest parties, even if the dealer is corrupted, is consistent with some secret S, even, which means that we want to have agreement among all the honest parties. Correctness means that for an honest dealer, all the honest parties are going to accept and have shares that are consistent with its input, which is the input S. The communication model that we are going to have, first of all, we are going to have pairwise private channels. So P1 can send a message to any other party privately, and the receiving party will know from which one of the parties it actually received the message. So we have authenticated private channels. And we also have authenticated broadcast channels, so I can shout in the room and everyone will hear me and everyone will hear exactly the same thing. So we have one channel out there that when I broadcast something, everyone receives the same message, and they also know who spoke, who gave that message, who submitted that message. So as a warm-up, I'm going to start with a VSS, again in the computational settings. Again, we have the alarm on the top of on the slide. So here I need a group of order Q with some generator G, in which the discrete logarithm is hard, and I have a random oracle H. And the idea is that the sharing algorithm now, in round 1, the dealer chooses a random polynomial. This time I'm not going to plant the secret as the constant term. Everything is random. Each party is going to receive a share. This is the share of party PI. In addition, the dealer also going to broadcast everyone here exactly the same thing. So this is what each party receives, PI receives in the private channel. Here it's going to be broadcasted. So I'm going to broadcast G to each one of the coefficients of the polynomial. So there are out there T plus 1 values, B0, G to the B0, G to the B1, and so on and so forth. Okay? In addition, I'm going to hide the secret using this random oracle XOR with random oracle on the constant term of the polynomial XOR S, and this is because we have some leakage on B0. This is why we didn't put S here. Instead, we're going to have another function for security. So again, so each party receives one share privately in the private channel, and there is a broadcast. These values were broadcasted. Everyone sees exactly the same thing. Here is my view. What these values allow me to do, given my share, and given these values, I can see whether or not my share lies on the polynomial that is in the exponent of these all values. Okay? How do I perform this computation? So I have the share. I can do G to the P alpha I. I am Pi. I do G to the P alpha I. And because we know all those values, if I take Bk and do it to the power of alpha I to the k, essentially what I get is G to this value. And this is exactly the valuation of the polynomial on my point, on alpha I. Okay? So I can see if my view, my concrete share, is consistent with what every other party sees, which is the broadcasted value that the dealer gave out. What happens if I see that it's not the same? What do I know? I receive the private share. There is some polynomial over there, and my point is not on that polynomial. What should I do? So I see that my point is not consistent with the polynomial that the dealer says that it's shared. So I'm going to complain. I'm going to tell everyone, wait, something is wrong. The dealer is cheating. My point is not on the polynomial. The problem is how can I convince other parties that actually I am the one who received the wrong shares, and it's not that I'm just a corrupted party that is complaining against an honest dealer. So we have now a tension whether the dealer is corrupted and actually provided me wrong share versus whether I am corrupted and I'm just complaining on an honest dealer. Okay? So I'm going to present some good or bad idea. How can I convince others that my share is incorrect? What do you think about the following idea? We are going to construct the protocol together. Okay? So let's think together. I see that my share is incorrect, and I'm saying, okay, I send each party in the private channel the share SI that I received from the dealer. Is that a good or bad idea? It's not the best idea. Why? Because I'm using the private channel. What does it mean? That maybe I send to you one thing, and to another, to you, I send something else. And so here we want to get agreement, so I should broadcast to everyone, wait, the dealer is corrupted, the dealer, I received the wrong share. So the second idea is I broadcast a complaint, and I hope that everyone will believe me. Too optimistic, too simplified, right? It might be that maybe I'm the one who is corrupted. I'm just disputing an honest dealer. So we need to do something more complicated than that. I broadcast a complaint, and if there are more than T complaints, then for sure the dealer is corrupted, and we can abort the protocol. What do you think? So this is true, right? Because if there are more than T complaints, what do we know? That at least the number of corrupted parties is T. If there are more than T complaints, at least one honest party complains. An honest party complains only if its share is not on the polynomial that the dealer says that this is the polynomial that we are using. And therefore, we know that the dealer is corrupted, and we can just we have an agreement, everyone will abort, all the honest parties will just output some default point on a default polynomial. The fourth one, I broadcast and complain, and if there are less than T complaints or most T complaints, then the dealer is honest and we can finish. Again, this is too simplified, and this is because it might be that a corrupted party complains against an honest dealer. And there are most T corrupted parties, so we might have less than T complaints, and we need now to resolve these complaints. We need to decide, when I see a complaint, whether it's true or not. Okay, so I'm continuing with the protocol. So if I see a wrong share, the dealer gave me a share, I checked it with the broadcasted messages. I see that my share is incorrect. I'm going to broadcast a complaint. I'm going to say, everyone, hey, I received the wrong share. Now we say that if there are more than T complaints, there are at least T plus 1, we can abort. The dealer for sure is corrupted. We don't have to deal with this case. But now, otherwise, what do we have? So I'm PJ, okay? I'm honest. And here I see the dealer is honest, and PI complains. Now I see that my share is okay. I don't know if that's a fake complaint, if that's the actual situation is, or we are in this case. I'm PJ, I see that my share is okay, but the dealer is corrupted, and PI actually honest party that complains against the dealer. There are two cases, we don't know which is which. So the way we proceed is that once someone complains against the dealer, and we are less than T complaints, at most T complaints, the dealer should broadcast the share of that party that complains. Okay? This is the next step in the protocol. And now you have to stop and ask me, why is that okay? Why it's okay to reveal a share of a party? Again, the adversary maybe learned some new information. It will just complain, and then shares will be revealed out there. Shares of honest parties. Okay? Is that possible? Does the adversary learn any new information from this stage? So the answer is no, and why is that? First of all, if an honest party, if we have an honest dealer, and PI complains, what I'm going to reveal the share of PI, okay? But the adversary already knew the share of PI. It's a false complaint. It received that share before, so it doesn't learn anything new. On the other hand, if we are here, then the dealer knows the secret. PI actually complains. PI, the dealer is corrupted. It knows what it already sends to PI. It knows the share it sent. Now this share is being broadcasted. It's exactly the same information. So it doesn't learn anything new from this thing, the adversary. Okay? So here the dealer broadcasts the share of each party that complains. And there are three options to consider. Once we broadcasted every value, every share of each party that complains, there are three options. First of all, we might see this thing, okay? It might be that the broadcasted SI looks okay, and I still don't know if it was a false complaint or not. The second case is that I'm PJ, PI complains, the dealer sent something, and this something was actually wrong. It was broadcasted, and I see a share that was sent, and it doesn't fit to the polynomial in the exponent that the adversary already sent. What does it mean? The dealer is corrupted for sure because it has something inconsistent that it sent on the broadcast channel. We can finish. And we can abort, and we have agreement because it all happened on the broadcast channel. All honest parties sees exactly the same thing. We have agreement. The third case is when PGI complaint, dealer provided true information, okay, the truth share, and so all parties sees that whatever the dealer provided on the broadcast channel is okay, and we don't know if it was actually a false complaint of PI or the dealer is corrupted. Okay, so we have two cases that we don't know what actually happened, but the answer is we don't really care. The only things that we care about is to reach an agreement. And we can reach an agreement, it just means that actually here in this case, when the dealer is corrupted, PI is honest. So PI received in the first message, it received something wrong, it broadcasted, hey, something is wrong, and then it received later something else was broadcasted, but now it was the truth share, the share that actually lies on the polynomial. So I just say to PI, you know, take the last share that was broadcasted. Take that share that was broadcasted as your point on the polynomial, and this is what you have to use. Okay? So this PJ doesn't know if this was the case or this was the case, if it was dealer honest, PI false complaint, or dealer corrupted, PI as a true complaint, but then the dealer corrected the share that it provided in the first place. Okay? And for us is that if all complaints were resolved and we didn't see something, we didn't meet that case that is deemed now, then for us there are no contradictions. So all honest parties hold shares on the same polynomial. We can also see it on the broadcast channel, and we are fine. So I just want to recap and give the entire protocol. So in round one, the dealer computes shares S1 to Sn. Each party receives Si on the private channel, and also the dealer publishes all the coefficients in the exponent on the broadcast. In round two, each party checks its share. If it wrongs, I broadcast complaint. Round three, if there are too many complaints, we are done. Otherwise, the dealer broadcasts the share of each party that complained. In round four, we just see how many, all parties verify the shares that were broadcasted here. And if something is, we have some contradiction, then everyone abort and output a point on a default polynomial. Otherwise, I'm going to accept, and I know that all on the other honest parties also have correct shares on the polynomial. Okay? Good. But here, as we said, we are using something, we are using computational assumptions, and our goal is to do it in information theoretic settings. Okay. So in order to do it in information theoretic settings, I want to introduce a new kind of primitive. And this time, it's going to be a bivariate polynomial. So what is a bivariate polynomial of degree t that hides some secret s? It's a polynomial that now has two variables, not only x, we have x and y. And it has in total t squared coefficients, t plus 1 squared coefficients. And I'm going to embed the secret as the constant term. Okay? And I'm going to do exactly like we had in the univariate polynomial. Here, I'm going to define a share of a party is going to be, instead of a point, it's going to be a polynomial on that bivariate polynomial. So each party is going to actually receive two polynomials. It's going to be the evaluation of S on alpha I, X alpha I, and the evaluation of this bivariate polynomial on this alpha I as the first term. Okay? I'm getting two polynomials. What's the degree of each polynomial? Each univariate polynomial? T. Okay? Once you put alpha, everything becomes just alpha, just T. Okay? So both are univariate polynomials of degree T. Fi is going to be my actual shell of Pi, and Gi is going to be another aiding polynomial for authentication. Okay, I'm going to authenticate other shares of other parties using the other polynomial, the G. Now, what is nice about these polynomials and this way we distribute this bivariate polynomial is this equation. And this is very important. So it's all that if I evaluate my polynomial, my authentication polynomial on alpha j, it's exactly like evaluating my friend's polynomial on alpha I. Okay, you see that? Because gi on alpha j is s on alpha I alpha j, and party pj received the polynomial fj of x, so when it evaluates it on alpha I, it's exactly my value. These are constants in the field, like distinct non-zero elements, like we had in Sherman. Okay, another way to look at bivariate polynomials is as follows. So we have this grid. The secret is here, S of 0, 0. And a share of a party, we look at this as a column. So I'm going to evaluate S of x on alpha 1. So these are the Fs. Okay, distinct polynomials. But then the G's are going to be verifications. So G is this polynomial. And now I have each party. Party P1 is going to receive this line and that line. And in fact, it's going to receive 1 point on each one of the other parties' polynomials. So each party receives 2 points, and as we said, Fi, for every pair of parties, Pi and Pj, they actually have 2 points in common. They have Fi alpha j and Gj alpha I, and they have Gi alpha j and Fj alpha I. 2 points in common. Just some more words about bivariate polynomials. So in order to reconstruct, what we need is just security. T points, in Shamir, T points didn't reveal anything about the secret. Here, T polynomials, T univariate polynomials, T columns they look completely random, exactly like in Shamir. Moreover, even a set of 2T polynomials, I give you the Fs and I give you the G. This is going to be the view of the adversaries in the protocol. If I give you F and G's like that, I give you only T of them, every secret is still possible. It still doesn't reveal you any information about the secret. In order to reconstruct and to interpolate the bivariate polynomial, you need either this T shares plus the secret S, or you need T plus 1 polynomials, Fj's. You need T plus 1 shares. Okay? So it's exactly like Shamir, but this time we're working in 2 dimensions, and those my share is a univariate polynomial and not just a point on a polynomial. And interpolation is the same. I need T plus 1 univariate polynomials in order to interpolate and get the bivariate polynomial. Questions so far? Okay. Also from the G's, yeah, it's completely the same. Yeah. Okay. And it's the interpolation is very similar to the Lagrange that we saw. We design a bivariate polynomial that agrees with the first chair, then with the second chair, and so on. And then we just sum up over all these bivariate polynomials. Okay, so the VSS protocol is as follows. So the first round, the dealer chooses a random bivariate polynomial where it puts its secret as the constant term. And each party, PI, is going to receive, using the private channel, two shares. One is this univariate polynomial, and the other is this univariate polynomial. Okay? Now, in the second phase, what do we have? So we got a lot of polynomials. This whole construction of bivariate, it gives us the ability to check that the polynomials that we got are somewhat consistent. How do I know that my share is consistent with your share? I can evaluate my polynomial on your point. I can evaluate my two polynomials on PJ's point, and I can tell it to you because you are supposed to have it anyway. So I'm going to tell you in the private channel what are these 2 points. Now, you are supposed to have exactly the same information. However, if it happened to be that what I do in the second round, for every other party, I'm going to evaluate my polynomial on their points. I'm going to send them what is the result of that evaluation. Okay? Now, every party receives 2 points on the bivariate polynomial. And they're supposed to be the points when it evaluates its polynomial on my value. So we can check. I can check that now I received values from all other parties. And if I see that party that I received doesn't agree with what I received from the dealer, I'm going to complain. So I'm going to broadcast a complaint, which means, again, if I received wrong values from party PJ, I see that something is wrong, and I'm going to complain, I'm PI, I received from PJ values that are not consistent, and I'm going to complain with the values that I actually received from the dealer and not what I received from PJ. Okay, I'm going to broadcast the information that I received from the dealer. This is important. Okay, let's see it back to the grid. Let's see what we had. So PI receives 2 polynomials, 2 univariate polynomials, this one and this one. The first round, this is what I received from the dealer. In the second round, to each party, I'm going to send to P1 these 2 points. To P2, I'm going to send these 2 points. Everything is still on the private channel. We still didn't use the broadcast. Okay? To all parties, I'm sending 2 points. Now also receive from each party 2 points on whatever their share when they evaluate these points on their polynomial. Now let's say that from P2, instead of receiving these 2 points, I receive these 2 points. Then I know that something is wrong. What I received, if we are both honest, what I received and what you received are not consistent. This is a problem. Or it might be that PJ is corrupted and is just trying to make some mess in this verification. So I'm going to complain, but I'm going to complain not with the values that I received. I'm going to complain with the values that I received from the dealer. Okay? Good. The next round. So the dealer now has to check the complaints. So for each complaint I, J, U, V, the dealer checks that whatever is out there in the broadcast channel, it's actually consistent with the true values that it sent. What does it mean? So remember that this is what I received, but I'm going to complain with the true values. And if it happens to be that these are the true values, this is whatever I'm complaining is whatever I actually send to that value, and whatever is complaining is correct, the dealer does nothing. The dealer say, this complaint is actually PJ's didn't send to PI right information, the correct information. On the other end, if the dealer sees that PI is now complaining with something wrong, that it's not the information that I sent you in the first round, what is going to happen? That I'm going to reveal the share of PI. And again, you need to ask, why is that okay to reveal a share of a corrupted of someone? Can the adversary learn something new? Okay? So this is exactly the same question as we had before in the computational setting. If the dealer is honest, we are always going to be an honest party will receive honest share. If it's going to complain, it's always going to be the right values because this is what the dealer provided, and the dealer never going to reveal a share of an honest party. On the other end, if the dealer is corrupted, then there might be a reveal over here. Okay? So the dealer never, the adversary doesn't learn any new information. Okay. Some questions. Again, just to see that we understood. So is it possible that an honest party receive wrong subshares from another honest party? So now we are in the case where the dealer is honest. I assume that the dealer is honest, okay? Let's see what we have. Let's analyze the protocol when the dealer is honest. I still did not provide the last step of the protocol. We are still building it. So what happens if the dealer is honest? Is it possible that an honest party receive wrong subshare from another honest party in the second step? Again, what are the subshares? So in the first round, I'm receiving these shares, and then I'm sending to each party subshares. I'm sending these 2 points, I'm calling them subshares. Okay? I send that to P1, that to P2, and so on. And now the question, if the dealer is honest, and if you are honest, and you are honest, everyone is honest, can it be that you received something that is wrong? And the answer is, of course, not. Honest dealer going to provide bivariate polynomial that is consistent, degree t. I'm going to send you correct shares. You're going to evaluate. Whatever two honest parties have are going to be consistent. Moreover, we are still in honest dealer. Will an honest party ever broadcast a complaint if the dealer is honest? Might I broadcast a complaint? Yes. And why yes? Because another party sent me something that is wrong, and because I saw something that is wrong, I'm broadcasting complaint. But when I'm broadcasting the complaint, I'm going to put the values that the dealer sent, and then the dealer says, okay, this is a false complaint, and it will do nothing. Will the dealer ever broadcast the shares of honest parties? Broadcast, reveal them? The answer is no. Why is that? When do I reveal? When the dealer reveals a share of a party, only if I broadcast a complaint and the values that I provide there are not the true values that the dealer sent me in the first round. Only then I actually broadcast, I reveal the message of the party, the share of the party. Okay. May the dealer reveal a share of someone? Yes, if some party is corrupted, it broadcasts a false complaint, but it puts wrong values as U and V. The dealer sees U and V, says, no, this is not what I submitted, then I'm going to broadcast the share of that corrupted party. Okay, if some polynomial is broadcasted, will it contradict a polynomial that is held by some honest party? Okay, what do I mean? The dealer now broadcasts a polynomial. Once it broadcasts the share, I can check, each party can check that the broadcasted information is consistent with the share that I received in the first round. And now I'm asking the question, if I see such a polynomial that is broadcasted, will it contradict the polynomial that I have? And the answer is, of course, not, because the dealer is honest. So the last round of the protocol is as follows. So each party, after we add all these complaints, and the dealer answered the complaints by either not answering anything if the complaint has the right U and V, or it might reveal the share if it has the wrong U and V. After the dealer broadcasted and answered all the complaints, there's going to be a vote. Each party PI, it's going to do the following. If there are joint complaints, PK complains against PJ, and PJ complains against PK. Okay? Then it must be, it cannot be that both are right and the dealer cannot answer one of them. It must reveal one of those shares, either PK or PJ. If it did not reveal one of them, then the dealer is completely dishonest. We can abort the protocol and reject. Moreover, for every value that every share that the dealer broadcasted, I can check if it's consistent with my polynomials that I received from the beginner. If I see something that is contradicting, I'm not happy with this, this message. Moreover, the dealer, there is again the case, as we had in the computational setting, that the dealer provides someone wrong share in the beginning, and then after all the complaints, it kind of corrects the share and broadcasts a new share to that PJ party. So if J equals I just update my share to be the new value, the new share that was revealed. What happens now is a vote. If whatever was broadcasted here in the reveal is consistent with my polynomials, and my share here was not updated, I'm going to broadcast consistent. I'm saying I'm happy with whatever I saw. My view is okay. On the other, if at least n minus t parties broadcasted consistent, then I'm going to output my share, and I know that this is the right. I believe that everything is okay. Okay? I know it's very confusing. It has a lot of steps, but let's try to analyze it. So we already said what happens in an honest dealer. In an honest dealer, will we have ever this case, that the dealer will not answer a joint complaint? No, the dealer is honest. If he sees joint complaint, two corrupted parties are going to complain against one another. I'm going to reveal one of them. There's no problem. Still honest dealer. Honest dealer, each honest party sees the broadcasted polynomials here, and they're always going to agree with what they have. Because the dealer is honest, whatever is broadcasted is consistent with the view of an honest party. Will a party ever has to update its share? Honest dealer. Well, that also doesn't happen. It's not never happens. In an honest dealer, I give you a share. The share is going to be correct. I'm never going to correct the share that I gave you in the first round. So in an honest dealer, we actually know that there are going to be at least, actually, all honest parties are going to broadcast consistent, okay? So we're going to have n minus t broadcasts, messages of consistent. What happened in a corrupted dealer? And what does it mean? The real question is, what does it mean that n minus 2 parties broadcasted consistent when the dealer is corrupted? What is guaranteed to hold? So the questions now is the case of corrupted dealer. Is it possible that an honest party received wrong points, wrong subshells from another honest party? Yes. And why? The dealer might send contradicting information to PI and PJ in the first round. N minus T parties voted consistent. How many polynomials of honest parties were replaced? When do we replace a polynomial? When we update a polynomial. Only I broadcast a complaint, and the dealer might reveal my polynomial to everyone, and then I might update it. I might replace it. How many? If n minus t parties voted consistent, it means that at most t honest parties were replaced, because, more importantly, at least t plus 1 honest parties received consistent shares already in round 1. If we all agreed, we did this voting and we got n minus t, it means that at least t plus 1 parties, we might have t votes of consistent from corrupted parties, but we must have a core of t plus 1 honest parties in the first round that received already consistent shares, and the shares were not replaced later on. Okay? So we do have a bivariate polynomial there already in the first round, in which, and we have a core of t plus 1 honest parties already in the first round, and the share is and the secret is already well defined. The bivariate polynomial is well defined, and all we do now in the next stages is to guarantee that all other honest parties will rely also on that bivariate polynomial. Last question, if only t plus 1 honest parties broadcasted consistent, does it guarantee that all honest parties hold shares on the same bivariate polynomial? And why is that yes? So when I broadcast a consistent, only I'm an honest party. I'm going to broadcast consistent only if whatever was revealed in the broadcast channel consistent with my view, okay, with my actual shares. So if t plus 1 honest parties broadcasted consistent, all the shares that were revealed are also consistent with their views, which means that we have a bivariate polynomial, all the shares of the honest parties, all the complaints were resolved, and all the shares that were revealed are also consistent with these t plus 1 honest parties. Okay? So this is the VSS. This is the sharing. I know it's very confusing, but now you can hopefully, if you read it, it will be much easier to read. I want to show another reconstruction algorithm for the case of bivariate polynomial. So if you remember, we had previously, we said if t is less than n over 3, we can correct errors on the polynomial, even if parties reveal shares later on that are not correct, we can identify them. When we have bivariate polynomial, it's even easier to do it. And I want to show how. So in the reconstruction, let's say that we did a VSS went well, and the dealer, we all have shares on this bivariate polynomial. In the reconstruction, each party can just publish his 2 shares on the polynomial. Now, it might be that some parties are going to reveal now wrong polynomials. They're going to send FIX that is not the correct one. It's not the one on the true polynomial. However, it's really, really easy to identify them because each Fi or each Fj is supposed to be consistent with at least 2t plus 1 g's. So all parties say all their shares, all their polynomials. So I'm supposed to be able to reconstruct to see that everyone is true. But I just look at the F's and I'm asking, is that F that was revealed by PI, is that correct or no? So I'm going to check it against all the G's. And if it has 2t plus 1 G's that are consistent with it, I'm going to say, okay, this F is correct, and add it to my set, and so on. Okay? So after I do this operation, I'm going to have at least 2t plus 1 correct polynomials, and I can reconstruct S. It's enough to have only t plus 1 correct polynomials. I don't need so many. And also know that this reconstruction requires just private channels. I don't really need the broadcast. I just send my polynomials to anyone else, and everyone can run this reconstruction. However, in many protocols, even though we do this VSS, we're using the bivariate polynomial. After the VSS ends, all the parties kind of forget what they saw and just outputs a point, the constant term, on each one of their F's, okay, on their F's, F polynomial. And this is the output of the VSS usually. Now, this corresponds to a degree T polynomial, which looks like that. So we said Fix is this thing. So when I output Fi on 0, this is what I get. And this corresponds to this polynomial. So all parties are actually outputting a point on a degree T polynomial, where this is the degree T polynomial, and its constant term is actually the secret. So what happens in many protocols that although we have this bivariate sharing and structure, we kind of forget it and continue like in Shamir secret sharing, and we know that we have 3t plus 1 points overall. 2t plus 1 are going to be fine at most t corrupted points. Okay, so for conclusion, what we saw is that there exists a perfectly secure VSS protocol in the presence of a malicious adversary. I want also to mention that if t is less than n over 2, there is also a statistically secure VSS protocol that has some error probability that is negligible, and this assumes broadcast. And that's it. Thank you.